Okay? So now you have concentration profile in the same manner as what we derived earlier for energy balance and for momentum balance. Once again, the whole system is defined based on experimental data. There is no theory associated with this picture. You just set up the experiment, try to see what happens, and then you try to fit the experiment data with some kind of simple equation. Okay? Any question for the moment? No? Now, the flux of A here that's going in positive y direction can be represented by WAY. WAY is the flow rate, mass flow rate of A in y direction. This is W, this is omega. It's different. See here? See here and there? This is W. This is omega. Omega represents mass fraction. W is mass flow rate. Okay? If you take mass flow rate divided by cross-section area, what you have would be a mass flux, right? It's a mass flow rate that's mass per unit time, per unit area that become mass flux. The mass flux of A from the bottom portion to the top portion depends on what? It's supposed to depend on or proportional with difference in concentration. The higher the concentration here, or the lower the concentration there, should give you a driving force for mass transport. All right? So it depends on omega A 0 subtracted by omega A up top here, which is 0 at this moment. Okay? This portion is driving force. It also depends on thickness of the system. If I have thick piece of glass here, the mass of A is supposed to go through slowly or in low amount, right? So it is inversely proportional to thickness Y here. Suppose this is Y. Okay? Now, you can say that it depends on mass fraction, difference. Or you can say that it depends on difference in mass concentration. Remember, we can express concentration in terms of both mass fraction and mass concentration. Mass fraction is omega. Mass concentration is rho. Okay? So that if I express them in terms of mass concentration, I can write down something like this, right? Rho A, total concentration times omega A, supposed to equal to rho A. Okay? Total concentration times 0 here, supposed to be mass concentration up there. All right? Now, I can change from proportionality to equality by write down WAY A equal to rho times omega A 0 subtracted by 0 divided by Y. And add one constant here. Changing from proportionality to equality, the constant here in this case is called D in script. Okay? And it's called DAB in this case. All right? In our system here, molecule A moves upward, and it moves slowly through a pores of this piece of silica. Sometimes it is called diffuse. So the phenomena here, sometimes people call molecular transport as diffusion. Okay? This is called diffusion. So what is diffusion? Diffusion is phenomena where mass creeping or transfer through a media without them flowing, without flow. And you can see that within our system here, there is no flow at all. The movement of molecule takes place molecularly. Okay? So imagine you have single molecules, and molecule itself collide with each other, and therefore it changes direction. Once it changes direction, it can go from bottom part of the system here upward. Okay? This is called diffusion. So our constant here, sometimes it is called diffusion coefficient. So if you have high diffusion coefficient, it means that the mass flux to be high number. So in any system where diffusion coefficient is high, diffusion can take place easily. That means mass flux by diffusion would be great number, right? So if you have high number diffusion coefficient, mass flux supposed to be high number. Physically, it means molecule of A can transfer to our system easily in great number. Okay? The equation here, once again, I like to emphasize, was obtained experimentally. We set up experiments, we observe what are factors affecting mass flux, and we come up with this equation. Okay? If you take the system, macroscopic system like that, and shrink it down to microscopic version of the system, then the constant here remains the same. But the difference, like this, if I shrink down the whole system to small layer, and this layer has the thickness dy. Okay? Of course, within this, the concentration at this part of the small system and upper part supposed to be different in very, very small number. So therefore, the difference here turns to be differentiation of mass fraction with respect to thickness. Okay? On the left-hand side, the flux itself, if you shrink down the system to be very, very small, then the flux turns to be another number. I mean, you may express the flux here instead of flow divided by area. You can use another term. Define the new term. Here is called JAY. So JAY is the flux of A, mass flux of A, in y direction. Okay? Now if you look into the sign or look into the direction, flux of A in y direction in this, according to this picture, is going in positive y direction. It's going up. So mass flux is going up. So mass flux itself is supposed to be positive number. On the other hand, the d omega by dy term here is the slope of this line. And this line has negative slope. Okay? So this term alone is supposed to be negative, but that term is supposed to be positive. The rest here are just constant, a positive constant. So therefore, in order to keep equality, you need to put minus sign over there. All right? The whole equation here obtained from experimental observation is called Ficks Law. Okay? It's called Ficks Law. Now, if you look into the unit, what is unit of rho? The unit of rho is kilogram per cubic meter. What is unit of JAY? It's mass flux, right? So mass flux is supposed to have unit of mass per time, per unit area. Okay? If you look closely in terms of unit, kilogram here is supposed to be kilogram of everything. This is kilogram of your system. On the other hand, kilogram there is kilogram of A. So these two units are not the same. Okay? What about unit of omega? Omega is supposed to have no unit. You have learned that mass fraction has no unit. But in fact, there is unit. The unit of the mass fraction is kilogram of A divided by kilogram of the system. So that's why this kilogram of system and that kilogram of system cancel out. Okay? Unit of Y here is meter. So in order to get unit balance, you find out that diffusion coefficient is supposed to have unit of square meter per second. Okay? And we have learned several times that there are more than one kind of variable with the unit of square meter per second. We have diffusion coefficient has unit of meter square per second. Mu here, do you recognize this variable? It is viscosity per density. It is called kinematic viscosity. Has also unit of square meter per second. Okay? Alpha, which is called thermal diffusivity. Definition of alpha is K over rho Cp. Has unit of meter square per second as well.